Get going. So welcome to my presentation, Expression-Oriented Programming with F#. I'm Robert Pickering. You can find plenty about me on the internet, so I won't go into who I am. So this presentation, I've done it a couple of times before, and the reception's been very different for the different audiences. The first time I did it to an F# user group and they absolutely loved it. The second time I did it to a more general conference and they weren't so keen. So I guess the aim of the presentation is to convert sort of imperative programmers to become functional programmers, but the effect it seems to have more is to reassure functional programmers that they're doing it right, but not so much convince imperative programmers they're doing it wrong. Anyway, we're going to be deliberately a little bit provocative, so I hope you're not easily offended. So without further ado, let's try and get going. So the first big assertion I'm going to make, and I hope it will become clear why I'm making this throughout the course of the presentation, is that programming is all about data, manipulating data. That's what computers do. They manipulate data. And that's, for me, what programming is all about. Now, some people seem to think that programming is not about manipulating data, and it's all about calling different APIs. Which is, I can see why people think that, but they're wrong. Okay, and the other thing I want to talk about, another assertion, is functional programming is not about programming without state. I mean, this is the thing that tends to jump to people's mind when asked what is functional programming. People tend to respond, oh, well, it's programming without state, which, you know, sounds a bit mad, really. How can you have a program if it doesn't have some kind of state? So I'm saying functional programming is not about that. What it is about describing the transformation between one state and another, and doing that in a way that is succinct and composable. We're also going to talk a bit about purity, which again is something that people tend to think of this very abstract academic concept, when in fact it's something that's really, really simple. Your function is pure if it only depends on the data that's passed into it. If it reads from its environment in another way, it's not pure. And this is going to be a talk about programming in the small. I like to think of programming in two ways. What you generally need is a high-level design which kind of gives you a roadmap of where you're going. But what I tend to find is you spend most of the day in the programming in the small bit, the actual writing the different codes, the expressions and statements you're putting together to do something. And in my experience, you tend to find at most conferences, people tend to talk about the programming in the large, the drawing big boxes, having components here, there, and everywhere. Whereas the everyday job of a programmer is spent much more time down here than up here. I mean, it's important to have that view of the world, but for me, this is the more important part of programming, the programming in the small. And it's that really the crux of the talk we'll talk about. I want to talk a little bit about the software crisis too, because A is a motivation for change, and why we might want to change. Now, the software crisis was something first identified in the 1960s. I think Frederick Brooks was the first person to talk about it in an academic paper called No Silver Bullets. And these are basically the points that he identified from it. Software is hard because of these four reasons. Complexity. Writing software is potentially something very complex. Conformity, that one's not so clear. What he meant by that was you generally have software that needs to execute in lots of different environments. You know, that was true in the 1960s when the paper was written, and it's true today, where you want code that's going to execute on servers, on desktops, on a multitude of embedded devices in the browser, etc., etc. Changeability, that's something very modern that well, it was relevant back in the 60s, but something still very relevant today. People always want changes. We're maybe a little bit better at managing that with Agile, but I think it still rests a problem. And the final one was invisibility, meaning that it's difficult to see what software's doing. I think this one's a little bit less relevant today. We have better debuggers, better ways of interrogating what's going on in memory, but writing software can still feel tricky because it's difficult to find out exactly what's going on. And I would argue that although things have changed enormously since the 1960s, we do still have a sort of software crisis in that we're better at delivering software that people want, thanks to mainly Agile. But the software that gets delivered is still very, very buggy. It works 90% of the time. You know, my live box at home falls all over all the time. My phone sometimes doesn't work as a telephone and needs a reboot. And there's just lots and lots of little examples like that. So now, moving on from the Brooks paper, there was another famous paper by Ben Mosley and Peter Marks called Out of the Tar Pit. And what they basically said in their paper is you can take all the four forms of software crisis that Brooks identified, and they all come down to complexity, different forms of complexity. And what they said is that software basically has two forms of complexity. Accidental complexity and essential complexity. Now, what they meant by this is some problems in software are hard. You know, if you're trying to do image recognition or something like that, signal processing, it's difficult, right? There's a lot of advanced mathematics and things like that going on, lots of data to deal with, so you've got interesting resource management problems. But some software problems aren't that difficult. You know, there are still a lot of developers out there writing sort of enterprise applications which basically just allow you to edit some data in a database. And yet, these projects go wrong too at a surprising rate. And for me, that is down to accidental complexity, complexity that is there in the system and there is no reason for it to be there. A huge source of accidental complexity, they argue in their paper, and for me, is state. And why do they say this? One of the most convincing reasons is this cliche: have you tried turning it off and on again? And it's a cliche because, you know, when somebody comes to you with a software problem, it's the first thing you say, and a lot of the time it works. And I think it's worth taking a step back to look at why it works. Most of the time, it works because the program has got itself into a unknown state. Some subtle invariant's been broken, probably something to do with multi-threading, and now it can no longer continue. And the only way to get it to work again is to reset everything back to a known good state, and the best way to do that is by restarting it. And for me, modern applications use far too much state. Now, I want to talk about why that is. So by classifying applications into the sort of the only three types of application you'll need to write. They're very kind of high level. But for me, you basically have command line apps, daemons and services, and GUI applications. So for me, it's kind of obvious that for a command line app that starts and executes, you're not really interested in its internal state. It's something incidental. What you're interested in is the actions that come as a result of executing it. What will a Git pushing something to a network, grep showing you a list of results in the console. So for command line app, state is totally incidental. I think most people would agree with that. Now for these, obviously you do need some state, but what I would argue is the way that we write them today, we use far too much state. So for these long-running applications, what you tend to see is applications written like this. So an event will come in, you'll process the event, and a result will come out. So if it's a GUI app, the event would be clicking on a button, you do some processing, and the result would be the interface would update itself in some way. And while you're processing the event in a sort of traditional imperative style, what you'll tend to do all the time is read and write to the environment. And I think a better way of writing these apps in a more functional style is to have the event that kicks off some reading from the environment, sucks in all the data you need to process that particular event, and when you've made all the computations to process this event, you spit the result out to the GUI or to the network or wherever, and at the end you write back any necessary data from the environment. So that way you're getting a lot less change in your environment, and the points where you're reading and writing it from, you can protect them much better because there's a lot less of them. So that's the kind of introduction and motivation for why we're going to do this. And now we're going to move on to the crux of the talk. So what is the difference between an expression and a statement? And it's basically, for me, it's the difference between a functional language and an imperative language. And by imperative language, I kind of group in most of the OO world with that too. So what is an expression? An expression is anything in a language that evaluates and returns a result. I would have loved to put up a reference to that statement. I searched quite a while for a precise definition of what an expression is. And I couldn't come up with anything, so that's I'm asserting that too. And I searched even harder for an explanation of what a statement is, but what most sources tend to say in a very roundabout way is a statement is just everything else. And so now I want to move on to a part of the talk where we look at the differences between expressions and statements. We're going to look at the difference between how you do same thing in C# and F#. The C# might as well have been Java, or could just about be C++ if you imagine a few more ampersands and stars. The F# could be OCaml or any other kind of ML, and it's going to be similar enough to the way you do things in Scala and Clojure. So basically, this is an if statement. It's a statement. It returns no results. We first initialize our variable, something that's in our environment that's going to hold a value. We then check the thing we're interested in, and if it conforms to our predicates, we read a value out of it, and then we push it into our pre-preferred location in the environment. Now, the functional or expression-oriented way of doing this is it's an expression. So rather than declaring a point in the environment first, we just have a name that's going to hold the results. And then in the first case, where our predicate conforms to the thing we want, we're okay, and we return a result. Otherwise, we return an alternative. And notice in this case that the argument can never go uninitialized, which is something that will save you a huge amount of problems. And when I show people this, they always say, yeah, but we have the ternary operator in our imperative languages, so we can do the same thing. Which is true to a certain extent, but the ternary operator is limited. If, for example, you wanted to do some intermediate processing in the ternary operator, impossible. You can't declare a new identifier within the scope of the ternary operator, which makes its usefulness limited, although I'm not trying to argue it is not useful. And the other thing they tend to say is, well, yeah, but how would you work if you wanted to to parse two arguments? So we've changed our predicates of it. We're making sure we've got two things, and then well, first of all, we declare two new points in our environment. We check we have everything we need, and then we unload, pushing the data into those points we prepared. And in fact, in functional languages, we have a very simple way of doing that. What we can do is we just return two values at the same time, a tuple. And then we can straight away unpack those values, or we could have captured them in a single identifier if we'd wanted a tuple. So the summary from that little bit is that if you're using a statement, basically statements trap data inside them, and they need to be pushed to a specific location in the world. And that's bad because it creates coupling between your computation and your environment. And we're going to see some other typical examples of this. This is a lock statement in C#. Basically, you need some declarations to lock on. We're interested in a collection, so we initialize a collection to read from. We initialize a point in the environment to be pushed to. That's the my data point. Then we take our lock, we push our data into that, and then we're free to use our data however we like. Our collection is protected. That's some pretty good code. But what we would do in F# is we see here that lock is an expression. It's just a function. It's not even built into the language. Had we had sort of lambda expressions in C#1, we might have seen them doing something a bit like this, more like this. There's no fundamental reason you couldn't do this in a language which you have lambda expressions in. So you just define a function, you pass your lock to that function, and then you pass in a lambda of what you want to do while you're inside that lock. And critically, the result of this lambda becomes the result of your lock function. So your lock function can return a value and can be captured in an identifier. No need to declare an identifier in a separate statement. And we see something very similar in the use binding. The using binding, using statement rather, in C#. So this was a very neat little functionality. It's combined with the iDisposable interface in C#, which for those of you that aren't C# people allows you to release resources in a sort of deterministic way. And what's going to happen is the use will just call dispose method to be called when it drops out of scope, so you don't forget to do your cleanup. And you know, for C#1 this was a great innovation. So this is showing some fairly typical connecting to a database. First of all, we need a connection, which is a resource, so needs disposing. Then we need to create a command, also a resource, needs disposing. So we have to declare our identifier to capture the data before all that. And then using always creates a new scope, so we're kind of getting all our getting all these new scopes opening and all our codes being pushed sideways. Which is, but we do get the nice deterministic deterministic disposal of resources. So Sorry, I've gone backwards rather than forwards. But the F# version is a little different because use is just a binding. It doesn't create a new scope. All we do is say use, and the compiler knows that when we want that to drop out of scope, when it drops out of scope, we should call dispose. So we can write the same thing without creating any new scopes. No need to declare our identifier way before it's actually being written to. So our identifier gets scopes in a much more sensible way, and we don't have loads of new scopes opened. So I guess the summary of all that is that statement-oriented program really emphasizes the slots in memory that you're reading and writing to, and it creates coupling between those slots every time you use one. Whereas expression-oriented programming really emphasizes the transformation of data from one type to another, and critically doesn't create that coupling between computation and a location in memory. There was a little quote from John Cormack, the creator of, founder of ID Software, creator of Doom, Quake, etc. He wrote a nice blog post called Functional Programming C++. I don't agree with all of it, because he talks at the very beginning how there's some great functional languages out there because you can't use any of them because the only language you can ever use is C++. Obviously not my point of view. I can understand him being a games programmer. He might think that. But a statement I found very interesting in it is refactoring towards purity involves disentangling the computation from the environment it operates in, which almost inevitably means more parameter passing. So the first part of the statement, fully agree with, and I would say that's a very positive thing, untangling the computation from its environment. The second part is also true, but critically, functional languages have lots of infrastructure to help us with this. Now, if you think about it, there's basically only two ways to get data into a function. Either you read the data from somewhere, which, as I'm saying, is bad, although it's necessary in a few places, or you have the caller of the function pass the data to you as a parameter. Now, as observed, this can lead to lots and lots of parameters, which is a big problem in F#. And a lot of programming is finding the correct way to tastefully group parameters together, in my opinion. But when you do have lots of parameters and lots of data being processed, functional languages provide something to help you. They automatically create closures. So what you could have is one big function at the top level that takes lots of data and then is broken down into sub-functions. And rather than explicitly having to pass these parameters to every little sub-function you create, they just all flow through, and the compiler will place a closure if it's necessary. So the workaround, people tend to do that in sort of object-oriented languages, is they use fields as an alternative. So they have the big function capture all the data, they unpack all that data into fields, and then they have the little sub-functions share that. And that can work okay sometimes, but you do get problems with scope that I will come to later. The other thing people do is you can use a function as a way of protecting an immutable data structure. So we can create this function that creates a buffer. We're going to do some work on this buffer, and shares it between lots of sub-functions. And we know that when we pass out of that function, the buffer will be no longer in scope. It might still be in memory. The GC will deallocate it. But we can be certain that it's not in scope anymore, so nobody can touch it. Now, The alternative in the OO world is to write that as a class and initialize your buffer in a class. And that can work very, very well until somebody comes along and decides that they want to cache this class because it's got a big buffer in it. Or they want to, and after they've cached it, somebody else comes along, well, let's make this multi-threaded. So then suddenly it gets accessed from several different threads. So the problem with fields is that it's very, very hard to reason about their scope because you have to reason about the scope of the class rather than the field itself. And it's also very, very difficult to tell whether they're being used from multiple threads because, again, you need to look whether multiple threads can access the class itself rather than the fields within it. Whereas if you allocate data within a function, you know that when the function's over, the data's either going to be gone away or you've returned it through its only exit point. So a quick word on testability. Anything that you write in this functional style will suddenly become very, very testable. You don't need complex mocking frameworks. You can just, because you know you're always going to get deterministic behavior if you just pass the data into a function, let the function do its work, and then you can do your assertions on the data that comes out. A quick word on type systems. The .NET type system guarantees that a reference will either point to a valid instance or null. So who can see the problem with that? Well, yes, it's the null reference exception. Now the F# type system, basically it tries very hard to get rid of the or null bit. It doesn't succeed completely, but if you write your code in this expression-oriented style, you'll find you just get many, many less null pointers because it forces you to think about what the alternative case is, and you can't accidentally forget and leave something uninitialized. So it does try very, very hard, although it's not technically part of the type system itself. So we've come to the end of the presentation. I just wanted to point out a couple of further reading items. I'm very fond of Thomas Pietrick's real-world functional programming in C# and F#. It's influenced my thinking huge amounts. There's a new book coming out. It's not quite out yet. Understanding Functional Programming. It's by a guy who's written a site, F# for Fun and Profit, so go and look at it there. Coming out very soon, I think, and will be excellent. Lots of good advice on his F# for Fun and Profit site. Just a quick advert for my company, RFQ Hub. We're a software house. We're looking for devs if you're interested. And so do we have any questions? We have 3 minutes left. Anybody? Well, if you're all being shy, I'll be around for the rest of the day and maybe tomorrow or Friday. And I'm also on Twitter. I'm very good at responding to questions on Twitter.